Now that we have classified our differential equations in a number of different ways, we're going to look at the concept of solving an ordinary differential equation. Now, we don't mean that we're going to cover that in this section, how do you actually solve it. In fact, that's probably the primary topic of this course, in addition to wanting to know how to use differential equations to actually model the real world around us. But for now, let's talk about what we mean by a solution. So I'm going to talk about solutions in terms of this variable phi. That's the Greek letter, which in some contexts you may refer to as phi, but that's a circle with a vertical line through it. That's what we call in a math class as phi. So let's say that's a function. Okay, so this is like the answer to the problem. We're going to say that that function phi is defined on some interval I, and it possesses at least n derivatives. So we're talking about an nth order differential equation. And those n derivatives are continuous. And when we substitute it into our nth order ordinary differential equation, it actually reduces to an identity, meaning that it satisfies the equation. In that instance, that's what we call a solution of the differential equation, solution of the equation on that interval. In other words, if this is your ODE, which you'll remember that's called the general form, then if I were to plug in phi of x into that, I end up with an identity, meaning it actually solves that equation. So this is just a formal way of saying that a solution satisfies the equation. Now, unlike whenever you're in algebra and you just plug in a number in for the variable and you see if it's equal on both sides, you sometimes have to take a little bit of work in order to verify that something is in fact a solution. So for example, let's say we have y is equal to e to the 0.1 x squared. We want to verify that that's the solution of dy dx equals 0.2 x and y. Okay, so in order to verify that, we're going to have to plug in on both sides. Plug in here and plug in here. Now, we know what y is immediately because y is sitting right there in front of us. Okay, but we got to know what dy dx is before we plug it in. So since we know y, we can actually calculate dy dx in advance. That is, find the derivative of this function. So you're going to use the chain rule. You're going to use the fact that the derivative of e to the 0.1 x squared is itself times the derivative of what's inside. So you'll multiply that by the derivative of 0.1 x squared, which is 0.2 times x. So you actually have 0.2x e to the 0.1 x squared. So that's what I need to stick in on the left-hand side and see if that's the same thing as what I get on the right-hand side. So plugging this in here and plugging in this for y right there will give me 0.2x e to the 0.1 x squared equals, and then I've got 0.2, I've got this x here, and then I've got this is y, so e to the 0.1 x squared. Are those two equal? Now sometimes you may have to do a little algebra to double check and show that that's an identity, but since that is in fact an identity, those are the identical functions on the left-hand side and the right-hand side, it is a solution. Solution, if I can write. All right. All right, now at this point, we have another example. We have y is equal to x e to the x. We want to verify that that is a solution of the ODE y double prime minus 2y prime plus y equals 0. So in order to substitute in, we're going to have to find y prime and y double prime. So let's do that off to the side over here. So y prime, the first derivative of this function, we'll use the product rule first times the derivative of the second plus the second times the derivative of the first, which is the same thing as x plus 1 times z to the x. Now I'll find the second derivative. I'm going to multiply or use the product rule again, so I actually have the first times the derivative of the second, which is x plus 1 e to the x, plus the second e to the x times the derivative of the first, which if I factor e to the x out of both of those, I get x plus 1 e to the x, or x plus 2 e to the x. So now we're going to plug those in up here and see if we get identically 0. So basically we're going to take y double prime, which is x plus 2 times e to the x minus 2 times x plus 1 e to the x plus, and then what is y? Y is x e to the x. The question is that equal to 0? Okay, so the left-hand side, if you multiply that out, you're going to have x e to the x plus 2 e to the x minus 2x e to the x minus 2 e to the x plus x e to the x. Right? Notice x e to the x plus x to the x minus 2x e to the x all cancel out. And 2e to the x minus 2e to the x cancel out also. So in fact, you do equal 0. Check. Okay, it is a solution. So notice, by the way, while this is a solution, y equals x e to the x, what about this guy? Y equals 0. Notice that y equals 0 is also, in fact, a solution to this ordinary differential equation, isn't it? If you plug in the second derivative of 0, derivative of 0 is 0. The second derivative of 0 is also 0. So 0 minus 2 times 0 plus 0 is actually equal to 0. Now, that's a very uninteresting solution, but it still is nonetheless a solution, which means we may be able to come up with more than one solution. That's a window into that idea that a solution may or may not be unique to the differential equation. Now, the 0 solution is often got the name of being called the trivial solution. Trivial meaning, yes, it's a solution, but it's very uninteresting. Now, if you think of phi, again, as the solution, remember phi is just my notation that I've used up in the definition for any solution, then by definition, the graph of phi, which is a solution of the ODE, we're going to call a solution curve, or sometimes it's called an integral curve. And we'll refer back to that reasoning here in just a moment of why it's called an integral curve. Actually, we may wait till next section. Anyway, that's the name of those graphs. They're called solution curves or integral curves. When you have a solution that has been solved for y, meaning that like the ones that we just did in the examples above, I had y equals some function. If that's the form that your solution is in, we call that an explicit solution. On the other hand, it is possible that in some cases that you will not be able to find an explicit form for the solution, but you may be given that the solution is in what's called an implicit solution, or that it is basically something that is not solved or cannot be solved for y. Okay, so implicit means that on some interval that phi of x would satisfy the relation ODE or the ODE. What I mean by that is, look at this example right here. If you verify that x squared plus y squared equals 25 is an implicit solution of this, what you're trying to show is that this has the property that it would satisfy this differential equation. Now, I can't easily just plug it in. What I've got to do is I've got to find dy dx, and the way you find dy dx for an implicit equation is to find the derivative using implicit differentiation. What is implicit differentiation? That's where you take the derivative of both sides of an unsolved equation. So you're going to take the derivative of this side with respect to x, and there's derivative of this side with respect to this. Something out of Cal 1. Although it was addressed again in Cal 3, so you've seen this before. Now, taking the derivative with respect to x means that when you got just x's, you just do the derivative like normal, so 2x. When you have y's, you got to do the chain rule. So the derivative of y squared is 2y times the derivative of what's inside. Now, why do we have to do the chain rule? Is because y is assumed to be some function of x. Now, we don't know what the function is because we haven't solved this for y, but what we can do is just put in there as a substitution or as a notation dy dx. That's the derivative of y with respect to x. So times dy dx. So basically that's how implicit differentiation works, is you take the derivative of all the x terms just with respect to x. If there's a y, you do it like it's an x, but then multiply times dy dx. The derivative of the constant is 0, so that's why the right-hand side is 0. Then I can solve this for dy dx. 2y dy dx is equal to negative 2x. I just moved this to the other side. divide both sides by 2y. The 2's cancel, and I end up with dy dx is equal to negative x over y, which is exactly what we're trying to show, so we did it. Now, we're not going to make a big deal about it right now, but at some point we're going to come back and address the fact of where is that function actually a solution, meaning that we typically will have information like this provided that tells us where, for what values of x, this is actually a solution. Notice, by the way, if you happen to recognize this equation, it is the equation of a circle whose radius is 5. So it's only defined. This curve satisfies this differential equation as on a range from x equals -5 to +5, as it is. Okay? Now, one of the things that we just saw is that a particular differential equation can actually have more than one solution. Now, one of those solutions was the less interesting case of the trivial solution, but sometimes you can have multiple interesting or non-trivial solutions. In fact, you can have whole families of solutions, and that comes in when you have parameters that show up in your solutions. So a solution containing an arbitrary parameter or constant represents a family of solutions, or in fact, we might even call it a set of solutions. And that's called a one-parameter family of solutions, meaning that your solution may have an extra dude in there that's just a constant. Okay, I'll give you some examples here in just a moment where you see that. Now, if you have n different parameters, it'd be an n parameter. So you can have 2-parameter families, 3-parameter families, 4-parameter families of solutions for particular differential equations, which means, again, you've got these arbitrary constants, the parameters that are in there, that you treat like constants, but it doesn't matter what number you put in for them. Anything of that form is, in fact, a solution. Okay? Now, here's what's interesting. A single differential equation will actually possess an infinite number of solutions. You know, we saw before, we checked one solution into one differential equation. Turns out that differential equation actually had an infinite number of solutions. Okay? Now, if you have a solution that doesn't have a parameter in it, like the ones we looked at before, okay. Now, I made no claim earlier that those solutions were all of the solutions, just that we wanted to check if that one was a solution. Now, here's the thing. If you have one like that doesn't have a parameter in it, that we just call a particular solution. Okay. Now, if a particular solution cannot be obtained by specializing any of the parameters in the family of solutions, then it's called a singular solution. For example, the trivial case is often a singular solution. Okay? Here is an example of a solution. Oh, don't know what happened there. Scroll back down, sorry. Here's an example of a solution that we're asked to verify. So this guy right here, claiming is a solution, and we're also claiming that this one is a solution. We want to show that both of these are solutions to this differential equation. So this is what I would call right here a one-parameter family of solutions. This is another one-parameter family of solutions, and we claim both of them solve this, which means no matter what C1 or C2 happen to be, if they're 2, they're 3, they're e, they're pi, they're any number, any constant, then it should still satisfy this. So let's check that. X now is our dependent variable and t is our independent variable. Let's find out what x double prime is in the first case. So we're going to let x equals c1 cosine of 4t to begin with. Then x prime is c1, derivative cosine is negative sine, so negative c1 sine of 4t, and you got to multiply times the derivative what's inside, so there's a 4 that's going to come out front, so it's actually negative 4c1 sine of 4t. The second derivative would be, the derivative of sine is cosine, so you still have a negative. you still have a 4c1, and it's going to be times a 4 again, so you actually get 16 c1 cosine of 4t. Now the 16 comes from the fact that you take the derivative of cosine, you get sine, but then times the derivative of what's inside, which is 4. 4 times that 4 out front here, it makes negative 16. Okay, now check. Plug that into this guy, right? We're plugging into this equation here, so we end up with x double prime, which is negative 16 c1 cosine of 4t, plus 16 times the original x, which was c1 cosine of 4t. Notice they cancel, and what do you get? 0. Checks. Okay, let's do x equals c1 sine of 4t. Then x prime is 4 c1 cosine of 4t, and the derivative of that is going to be a negative 16 c1 sine of 4t. Again, because the derivative of cosine is negative sine, that's the negative, times the derivative of what's inside gives me the 4 out front. 4 times 4 is 16. So now we plug that into the differential equation, and we'll see we've got x double prime, which is negative 16 c1 sine of 4t, plus 16 times x, which our x now in this case is c1 sine of 14. They're plus and minus, they cancel, you get 0. They are both in fact solutions. Another curveball I could throw at you would be to provide a little bit more complicated form for the y function, whereas before it was y equals some formula of x, some function of x. In this case, I can actually verify that a piecewise defined function is still a solution to a differential equation. So you got to remember how you work with the calculus of a piecewise defined function. It's actually pretty simple. What you do is to take the derivative of y, you take the derivative on each of the pieces. And then you got to be careful about what happens at the break point, because if there happens to be a corner at x equals 0 here, remember corners don't have derivatives because they have to be smooth in order to be able to have a derivative. But you can quickly check that. In fact, I'll show you. If you want to satisfy this differential equation, we need to know y prime. To take y prime, you just take the derivative of each piece. So for x is less than 0, we would get negative 4x cubed. For the derivative is greater than or equal to 0, but because we don't know what happens at the break, if it's the same, derivative is the same on both sides, then you just take the derivative of the piece and leave out the or equal for now. And then check, are they the same from both sides? Meaning, if I plugged in 0 on this one and 0 on this one, do I get the same thing? And since I get 0 in both cases, then I can include that. Meaning, the derivative is the same from both sides of that piece. Now, how do I plug in a piecewise function into this? Well, if you have xy prime minus 4y and you want to plug in this, well, you have to plug in each piece for y prime and for y, right? Because y has two pieces, y prime has two pieces. So for the top piece, where x is less than 0, if I plugged in this for y, meaning the x, negative x to the fourth, and plug in negative 4x cubed for y prime, I get this. X times negative 4x cubed minus 4 times x to the fourth negative. Right? I plugged the top pieces into this equation. For the bottom piece, x greater than or equal to 0, I would have x times y prime, which is 4x cubed, minus 4 times x to the fourth. In both cases, this turns out to be, well, this right here turns out to be 0. This one here turns out to be 0, which means both of those are equal to 0. So it checks. That is, in fact, a solution to that differential equation. As it turns out, y equals cx to the fourth is also a one-parameter family of solutions to this. So y equals cx to the fourth, you could check pretty quickly that that's a solution. But this is also a solution, but this is not a case of this. Right? You can't plug in a c in here and get this, which makes this equation here, I keep pointing at the wrong one, this one right here is a singular solution, meaning that it's not a special case of that one parameter family, so we call that singular. Not the same concept of singular that you learn in linear algebra in this case. So we're talking about singular solutions, mean they are solutions alone that don't have to do with a particular parameter family. Now the last thing I want to talk about in this section is what we call systems of ODEs. A system of differential equations is two or more equations that involve the derivatives. Okay, so when we talk about systems, we're talking about things that look like this. dx dt is equal to, say, 2x plus 3y plus 4t, and then say dy dt is 3x minus 2y plus 8t. So treating those two together as one model, one differential equation system, when we look for then solutions to that, we're going to talk about solutions to the whole thing. All right, now I'm sorry I dedicated a whole page to this one blank. I should have been more careful with my saving of the environment, I guess, and not waste a whole page of paper here. My apologies. All I wanted to say with this last blank is that the solution of a system is a set of functions defined on a common interval I that satisfies the whole system. So if you have a system of equations, you have to check that your solution, your x and your y function, would satisfy every equation, both equations in your system. Okay? So with all this extra space down here, I'll just say adios, the end. That's all for this section. Don't forget your homework is posted in Blackboard, so you can begin working on section 1.1 for next Friday.